Okay, so now I want to write the one expression version, but according to this, adapted to this situation. So adapted to this situation. So we know some things here. What do we know? What do we have that we can plug into this thing? Delta x is what? 0.5. What else do we know? A is 0. What else do we know? So this little r just stands for any generic rate function. We have, ours is called capital R, okay? So this AX is the same as J equals 1 to what? Floor of X over 0.5. A is 0. Delta X is 0.5. Capital R of A is 0. So J minus 1, delta X. And delta X is 0.5 times 0.5 plus capital R of everything else is the same. Ran out of room. So that, the piecewise one that we did a couple weeks ago, building up the linear piecewise function, now we have the one expression that can do it. All in one expression. Questions?
For the A of x, like,
Yeah.
do we have to put the less than or equal, or less than s, less than or equal to, for every single line?
Yeah, I didn't have room. It's going to be the same ones as the ones on the left. Same intervals.
Wouldn't it be more true to define it as the second line as a plus a of 0 and define it as 0.5?
No, so this is, yeah, someone else had the same question. How did that work? Remember, you're taking all the accumulation from the previous intervals, and now you're adding new accumulation in the current interval.
Right, but 0.5 isn't included in that first interval. 0.5 has a new rate. So if 0 is less than or equal to x is less than 0.5, and the next line would be.
Oh, you're talking about the less than or equals.
Right, and then right, but if we're defining it like that, we're defining it as plus a of the previous set of the previous set that had a different rate.
Okay.
Therefore, it would be a of 0.
No, but a of 0 is 0. There's no accumulation in 0.
We're defining it, we're still defining it as a certain rate. We're defining rate of 0 as whatever rate that is.
Right. But a of 0 is the accumulation of weight at time 0. A of 0 is the accumulation of weight at time 0. What is that? 0. Has there been accumulation of weight in the first half second? That's what we need to add to the new. A of 0 is there's no accumulation at 0. So yes, some people are noticing that there's a problem with the less than or equal to's and less thans. So I was writing it the way we normally do it, but if you use left, you have to switch them, okay? So that's fair. But the accumulation in the second interval is all the accumulation in the first interval. That's a of 0.5. That's a of 0.5. So the problem is that 0.5 goes into the second line. Yeah, so there's a little bit of a problem. But the idea, just think of the idea that you need all the accumulation in that first interval added to whatever new accumulation you have, k delta x. Right? So yeah, so in spirit, this is right, and that's what we care about, okay? So there's an issue with the less than equal to. You can, so if I don't want to focus on that. Don't let that distract you. The spirit of this is that you have all the accumulation in the first half plus the new accumulation in that whatever accumulation you have in that second interval, k delta x. Right? I'm right? Okay. All right. Okay. Okay. So, questions on this? Questions on that? Okay, so now we want to try to make a rough sketch based on these rates, you've got R0, R.5, and you just get a sketch of what you think the approximate accumulation function will look like based on those constant rates. So you try that. So try that upper right-hand corner of the first page. See if you can predict. I'm going to turn on the accumulation function, basically the one I put a box around, and it's going to draw the graph. What will it look like? Can you do it? Where are your sketches? Just a rough sketch. The idea of that graph on the right, what will it be? Yes. For half a second, you accumulate the cycle this rate. The weight of the sand you accumulate in the first interval. A of 0 is 0. A of 0.5 is the same question you had before 2 years ago. So new y equals old y plus new y. Old y is also how many of you got it before I showed you? Okay, how about that? A lower rate, then a higher rate, then an even higher rate of change, and then a lower rate, and then a lower rate means it's always positive. The rate of change is always positive. It's just going up slower at first, and then more quickly in the middle, and then continues to go up more slowly. You think about the sand dumping out. A little bit trickles out, then most of it, and then the last little bit trickles out. Okay, so we got to move a little bit here. Turn the page over. So we want to focus on x equals 1.35. 1.35 seconds, okay? So we can plot that point. We'll do this together. We'll plot that point on the rate graph. And we'll plot that point on the accumulation graph. Is this an approximate or exact accumulation? Because it's based on step, it's approximate. So we have that point there, which is 1.35, and A of 1.35. Okay? 20 seconds. What does that point mean? Tell the person next to you. What does that point mean? Go. What does it mean? Okay, what it means is at 1.35 seconds after the unloading started, there was a total weight of approximately A of 1.35 pounds of weight on the scale, right? So 1.35 is the time since we started unloading. A of 1.35 then is the total weight accumulated approximately in those 1.35 seconds. Hopefully you said something like that. Okay, so I want to work on how does this generate that value. We want to get this number. How many pounds? We want to know how many pounds are on the scale at this time. How does this thing do it? So we're going to break it down and get that value of A of 1.35 using this. How does it do it? We got 5 minutes to do it. Here we go. How does it do it? Well, it starts with this right here. What does this mean? What does this mean right here? Sum. So J is going to start at 1. It's going to give us what? An amount of accumulation for J equals. What does J equals 1 represent? What does it stand for? First interval. First interval. So here's our J. In the first interval, what was our... So in the first interval, what is this right here? Is it 0? According to our step rate function, is this 0? Well, let's do it. So R is going to be R of 0 plus, what's J minus 1? 0. So it's going to be 0 plus 0 delta x times delta x. Is that 0? No. Look at the first constant rate. It's not 0. Okay? So this whole thing right there is R of, so it's R of 0 times 1/2. That's what that thing does right there. When J equals 1. Okay? What does it equal? So I told you what R of 0 was. I gave you an approximation. So I said it was 0.211. So we're going to take 0.211 that I told you times 1/2. And what do we get? You told me already. 0. What is that? What is that? 0.1055. What does that number mean? Yeah. And what are a little bit of y? What's a change in y? What does that mean?
Accumulation of the sand.
Weight. That's the approximate weight accumulated in the first interval. When J equals 1, it just did R delta K delta X. Right? Okay? J equals 2. We're going to have, when J equals 2, we're going to have R of A is 0 plus, what's J minus 1? 1 times 1/2 times 1/2. So it's going to be R of 1/2, or this step right here, R of 1/2 times 1/2, or 0.5, sorry.
There are a couple of parentheses missing.
A couple?
And yeah.
Thank you. So A is 0 plus J minus 1. We're in the second interval now, so J minus 1 is 1. So 0 plus 1 times 0.5. That rate times 0.5. And what did I say the rate of 1/2 was? 2.225. So we get 1.1125. What is that? What is 1.1125? It's R times K times delta X. K times delta X. So it's the R function, our second step rate, times delta X. Okay, now what happens next? Do we have a J equals third interval? No, because the left-hand side, this sum is for what? Completed intervals. So how many completed intervals do we have when x is 1.35? 2. So now we're in the third interval, and where do we go to now? This part. So how much accumulation do we have for this partial interval, our third interval? So what is left of x? Our x is 1.35. What's left of x? 1. So now we have the partial interval here. So it's not j anymore. So the partial interval will be r of 1. That's left of 1.35 times the current value of x minus 1, which is 0.35. That's the width of this partial interval times its rate, which is that third rate up there, which I told you was at 4.88. So we need 4.88 times 0.35. Anyone got it?
1.708.
Oh, I love it. 2 people with the same number very quickly. That was great. Okay. So what is a of 1.35 then? See that the summation gave us the complete intervals, the little bit of change of weight, the little delta y, the little bit of accumulation for the first interval, for the second interval, and then for the partial interval. What is, so how does it do a of 1.35? Adds those together. Little bit of change. So how do things accumulate? Bit by bit. K delta x plus k delta x plus k delta x. What's the sum? 2.926. Actually, this is 100 pounds. So all these numbers are in hundreds of pounds. So 292.6 pounds. So let's check it. I'm going to go to graphing calculator here. I'm going to come down here. I have the acceleration, or there's the accumulation function. If I put in 1.35, let's see if we did it right. 2.9259. Can you see it? Got it. Check Blackboard for weekend tasks. Check Blackboard.
I think the computer